Okay, we're gonna pick it right up where we left off. You guys can figure out how I'm doing this right now, right? Just keeping it going. I find a song that I like, and we're gonna keep it going. Okay, cool. So let's review some of these learning goals here. So that first lecture, right? We talked about the Rutherford model of the atom and all of the scientists that contributed to that. Don't worry about knowing dates or names or where the people are from, but you should understand the structure of this atom and its basic components. Okay, we talked about isotopes and how to distinguish them using mass number, atomic number, and atomic symbols. Remember, atomic number, number of protons; mass number, number of protons and neutrons. I didn't say in the previous lecture, but I do not expect you to memorize the periodic table. I think that's kind of an old school thing that people used to do to torture chemistry students. You do not have to memorize the elements on the periodic table. But you should know, here, look, this is going to come in this lecture. Be familiar with the periodic table and its various regions. So I do expect you to know the various regions of the table, but not memorize all the elements and the symbols. The more you do chemistry, the more you'll know those things. Okay. So understand the difference between exact mass and average mass. I think we talked about that pretty well. So exact mass is it's the exact mass of each of those individual flavors. But remember, if I go and scoop up a collection of atoms, I'm going to have a random sample of isotopes based on the natural abundance, right? I shouldn't say it's random. It'll seem random to us. But if I go and scoop up a sample of carbon anywhere in the universe, roughly 99% of it is going to be carbon-12, okay? So those natural abundances are, for the most part, universal, okay? So calculate average or exact mass as well as percent abundance. So I just showed you how to calculate the average mass, okay? But consider that's an algebraic equation, right? So if you knew what the average mass of something was, you could also calculate the exact mass. And so just to review, right, this calculation we did on that previous slide, right? The average mass, so I'll add to that. So the average mass is always going to equal, the percent abundance times the exact mass, okay, plus the percent abundance times the exact mass. And so here I just showed you like if there's 2 isotopes, but if there was like 4 isotopes or 7 isotopes, we would just keep doing this for all the isotopes and all their natural abundances, okay? So if I knew what the average mass was and I knew what the percentage, let's say, I could ask you to solve for the exact mass for only one of those ions, all right? So I think there's some example problems of that in your homework, okay? So now we're moving on to this next stuff here. Be familiar with the periodic table and its various regions. And so this is where we're going to focus on in these next lectures, okay? So I'm going to come back to this at the end, this nucleosynthesis 2.9. I'm not sure why I put this right here. Let's keep going with talking about the periodic table, okay? So it was actually Dmitry Mendeleev, who arranged the first version of the periodic table. Pretty amazing, because there was lots of holes and gaps, right? Like you can see there's some gaps right here, but was still able to determine where these like undiscovered elements should go based on periodic trends. Okay, we're going to talk about periodic trends for the next year and how Mendeleev, amongst others, were able to discover these periodic trends. Okay, so but what I have now, I'm going to go at the very end of these slides. I put in a generic-looking periodic table here, and some of you are going to have really fancy-looking periodic tables. Some of you are going to have really generic-looking ones. I think it's important to be able to look at like one of the simplest periodic tables and still know what's going on, what all this stuff means, okay? And so I'm going to come back to this slide quite a bit, but the first one I want to point out, I know it's kind of small, but look, I'm going to circle this, carbon, and look, it says 12.011. So in that previous lecture, we calculated the average mass to be 12.01. And obviously, if I had more significant digits, we could have gotten to that 12.011. So that's the first thing to take note of. All of these masses, look, nitrogen, 14.007. Hydrogen, 1.008. I realize they're hard to see. So find a periodic table, right? Find a super high resolution, fancy, interactive one. I don't care. Find one that you know how to use, okay? But understand what all the things are on it. So first thing now that we should understand, this number here with all the decimals, those are the average masses. So we don't see from this simple periodic table what the natural abundances are of the other flavors. But what we should take note of, look at this number right here. 1 for hydrogen, 2 for helium, 3, 4, 5, 6. That's the mass number, okay? And what's the mass number again? Oh, excuse me. I said that wrong. I said that wrong. All of you people on the internet are freaking out right now. The atomic number, excuse me. That is the atomic number, which gives us what? That's right, the number of protons, okay? And so you can see it just counts. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? It's in order of the number of protons. So on this very simple periodic table, we don't see the different flavors. We don't see the number of neutrons. However, something I want you to be familiar with. Look, if I see that this mass number, atomic number is 6 protons, and I could see the average mass of this carbon is 12.011, call it 12, that tells me the most common flavor of carbon has to be carbon 12, because the mass is very close to the number 12, okay? Similarly, oxygen, look, 15.9999. That tells me the most common flavor of oxygen is likely to be oxygen 16. And so what I can do from there, so if it's approximately carbon 12 and there's 6 protons, that means the most common flavor of carbon is carbon 12 with 6 protons and 6 neutrons. Okay, same with oxygen. If we see here 8 protons on oxygen and its mass is roughly 16, 15.99, right? Then that tells me the most common flavor of oxygen is oxygen 16, 8 protons, 8 neutrons. And we'll go back to that sodium example that we did earlier. And I know these are small, so hopefully you can zoom in and find a periodic table that you like. Sodium 11, 11 protons. So we can see the mass is 22.99999 something. That means the most common flavor has to be sodium 23, 11 protons, 12 neutrons. Some of these are a little bit more difficult. Like, let's look at chlorine. Chlorine is 35.45. So the fact that that mass is like 0.45, that tells me it's hard to say if the most common flavor is 35 or is it 36, right? So when we see some of those masses that have decimals that aren't easily rounded to a whole number, that tells you there's quite a bit of a distribution of different flavors, and that's interesting, okay? So let's go back now. Okay, let's keep going. Okay, so now the various regions of the periodic table. So this was Mendeleev's, early periodic table. We know now we see it something like this, okay? So periods go across this way. Groups go down like that, okay? So I want you to know the name of these groups. That's part of the learning goals, knowing the various regions of the table. So group 1, this very first group, right, that would contain hydrogen. Well, hydrogen's not a part of it, right? But hydrogen's right there. But lithium, sodium, etc. Those are called the alkali metals, okay? Group 2, the next row over, okay? The alkaline earth metals. I should really say the next column over. Alkaline earth metals for group 2, okay? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Group 17 are the halogens. Okay, and hopefully you know group 18 are the noble gases. Okay, there's a lot more on this, but we're just putting it up, starting simple for now. Group 1, alkali metals. Group 2, alkaline earth metals. Group 17, halogens. Group 18, noble gases. Okay, here's a little bit more of that. Okay, so, right, group 1, group 2, 3, 4, 5, 6, etc. So now here's a little bit more information on this table, and here we can see the nonmetals, metals, and metalloids have been separated. So many of you know the very famous stair step, right, on the periodic table that separates the metals from the nonmetals and the metalloids. Okay. So you can see the nonmetals by far are outnumbered by the metals. There are far more metals in the universe than there are nonmetals. Okay. This interesting region right here, just these handful of metals, or really metalloids, right? We'll talk about these later on in the semester as when we talk about semiconductors and solids. Okay. And hydrogen, right? Hydrogen is kind of weird. You know, it looks like it should be a part of the alkali metals, but hydrogen stands on its own, right? It is really a non-metal. Okay. And then, of course, we should recognize this top group, the lanthanides, and this bottom group, this top period, the lanthanides, and this bottom period, the actinides. Okay. So, and you can see their properties, right? Metals, shiny, solid, conduct heat and electricity, malleable, ductile. So malleable means I can bend it. Ductile means that I can form it into different shapes and it still holds its structure. Solids, liquid, gases, okay, for nonmetals. The solids, the nonmetal solids are brittle. So don't confuse that, right? We can still have a solid that's a nonmetal. Think about, sorry, I just completely blanked out. Think about carbon, okay? Carbon is a nonmetal, but we can still have a solid form of that, all right? Okay, and then the metalloids, shiny like metals, but they're brittle like nonmetals, and they're what we call semiconductors, okay? Let's keep moving on. So now, another way of thinking about these atoms on the periodic table. So the main group, what we call the representative elements, so the things that you're more likely to come in contact with in your life, are group 1 and group 2, the alkaline earth metals, as well as this block right here that I'm going to later on in the semester call the P block. Okay. And now we know everything in here is, or not everything, but most of everything is the transition metals. Okay. And we'll get into why those are special. Okay, so let's get into some trends in compound formation, all right? So we talked about the structure of the nucleus, the protons and the neutrons, and that's what makes unique atoms, and then, of course, unique flavors of those atoms. But it's really the way that these atoms form compounds, the trends, that give them their unique chemical properties, okay? And that is all about the electrons, okay? So I'm gonna write all about the electron. So this is symbol for electron, okay? When we get into the trends of compound formation. So for example, if I look at sodium here, and you notice that in this reaction, we've got the mass number and the atomic number, but that doesn't change the number of, the number of electrons don't affect those numbers off to the left, okay? So I can still simply write sodium, so neutral sodium, right, which we know is going to have 11 electrons, and I know it has 11 electrons because it's not charged and it has 11 protons, okay? So that number, right, tells me 11 protons. So now, when sodium loses one of those electrons, it becomes sodium plus. We call that a cation, not a cation. cation for positive charges. Now this sodium plus cation only has 10 electrons because it lost one. And the reason why it's not positively charged is because it still has 11 protons, but now it only has 10 electrons. So if it has 11 protons and 10 electrons, it has to have a positive charge. Okay. Well, what about chlorine? Well, chlorine, we recognize, because it has 17 protons right there, has to have 17 electrons. But now if I add an electron to it, right, this is still going to have 17 protons, but now it has to have 18 electrons. So 17 protons to 18 electrons means it is -1. And we call that an anion. So cation's positive, anion's negative. And if I combine these, a sodium plus and a chlorine minus, they're like two peas in a pod. Opposites attract, right? It becomes sodium chloride, which I'm going to put a little indicator there for solid. And this is what a sodium chloride looks like. Okay? The sodiums are orange and the chlorines are green. We'll learn throughout the semester that the cations become quite small and the anions become quite large. Okay? And because of the way that these are positive negative, they have to be they have to alternate. You can't have two positive sodiums next to each other, or two negative chlorines next to each other. So it's got to be like, you can see they're diagonal, right? But they still have positive negative, positive negative, positive negative. And because of that arrangement of these ions, it gives it its bulk crystal structure, which is pretty cool. So sodium chloride on the bulk looks like a cube, a little crystalline cube. That's because if you shrink yourself down to the size of one of these atoms, it is cubic with the way that these atoms pack together. We'll explore this more throughout the semester. Okay. So what we just described was ionic compounds. Compounds that form because of the mutual attraction between opposite charges. So we'll say mutual attraction of opposite charges. Okay? Covalent compounds, on the other hand, form from sharing electrons. Okay? They are covalent. So I know valent might not be obvious what that term means, but you could think of it as like codependent, right? The compound cannot form if it did not depend on the other atoms. So the other atoms depend on each other to form this compound. They're covalent. Ionic compounds, on the other hand, only form due to their mutual attraction from opposite charges. Okay? So there's a huge difference between this, and we'll spend a lot of time going down this rabbit hole discussing this. Okay? Okay, so based on the position of an atom in the periodic table, we can predict what its likely charges will be when it forms a compound. Okay? So I'll say that again. Based on the position of an atom in the periodic table, we can predict what kind of charge it will have when it forms a compound. All right. So, for example, what do you notice about group 1 here? They're all +1, always. Okay? Group 2, all +2. Okay? So we can start to say that. All 1+. All 2+. Another one that we can definitely say, the halogens, when they form compounds, all 1-. So we can count on those, and I think, I might have that in a summary slide coming up. Okay? So group 1, we can always pretty much count on them being all +1. Group 2, we can all count on those being 2+ for their charge. Okay. The halogens, we can all count on being -1. And then now here's where things start to change. Okay. So you notice oxygen, sulfur, selenium, and tellurium are all -2. Okay, we can expect that usually most of the time. And you're going to hear me often say chemistry is the science of exceptions. So there's a lot of exceptions to these rules we're going to have to learn. But for now, we'll take it one at a time. Okay, so you can see these 4 are almost always 2-. So we can kind of think of it as 0, -1, -2, -3 for nitrogen and phosphorus, but not for anything else in this group 15. Okay. Similarly, now if we look at group 3, scandium and yttrium are 3+, and titanium is 4+, and so forth. But now look what happens with vanadium. Vanadium can be 5+, but it could also be 3+. And look what happens with chromium. It's not 6+, it's 3+. And manganese can either be 2+ or 4+. Okay, so these transition elements that I'll box up right here. For now, I'll just box these, right? They can be variable. So when they form compounds, their charges are variable. You don't have to memorize them if you know how to figure out what it should be. And we're going to spend a lot of time going through that. But you still should have some kind of familiarity with the common flavors. Iron is almost always 2+ or 3+. Rarely, if ever, would you see iron 8+, for example. Similarly, copper +1 or +2. Rarely would you ever see copper as 4+, for example. Okay. So, but as we go through this, there will be some that I do expect you to know, and some that I expect you to be able to figure out. Okay. So let's go through that. And so, excuse me, I'm going to circle in red some of the ones that I think you should know. Okay. These ones. And these ones. These you should know. Okay. Red is stuff you should know. These ones. All right. I'm going to erase this line so it's a little bit more clear. Okay. These 3 you should know. Because aluminum is always 3+, gallium is always 3+, and zinc is always 2+. Okay? And these 2 I want you to know. Silver is always +1, and cadmium is always +2. All right? But for example, like this lists titanium as 4+. There's also other flavors of titanium. So this isn't showing you everything. But what I've got in red now, red, you should know. Okay? So these areas, you should know these charges. All right? So let's move on. Okay. So now we're going to get into this naming compounds, and let's see. I think what I'm going to do, I know I'm just like cruising through this thing. I'm going to record a 3rd and final video for this week that's all about naming compounds. So this one was kind of short and the first one was kind of long. So expect that. But now because naming compounds is going to be a fairly large process, I'm going to record a separate video just on naming compounds. Okay, so let's talk about what this video covered. Okay, so we talked about the different regions on the periodic table. I know I went through that kind of fast, so make sure you are spending plenty of time with the periodic table. Find a periodic table you like, save it, download it, marry it, love it forever. It will be your guide through this class. Okay, know the difference between ionic compounds and covalent compounds and how they are constructed from the periodic table. Okay, so let me go back to that just a minute and speak on that. Okay, so ionic compounds, all right, I think I can add to that. Yes. Okay, so an ionic compound is always a metal for the cation and a nonmetal from the anion. All right, So a good way to think of that, if I go to my periodic table here, right? Ionic compounds are always going to be from like the leftmost side of the periodic table with the rightmost side of the periodic table. Okay? So let's write that down here. We'll say cation equals a metal. Anion, sorry about that. Let me write this a little more clear here. Okay, we'll say cation equals a metal, and anion is a nonmetal. Okay, what about covalent compounds? So let's see here. Okay, here we go. Covalent. Compounds consisting of two non-metals. So let's write that down on the covalent compounds. Covalent compounds, all non-metals, and there's no cation or anion because these are sharing electrons. They're not becoming charged species, okay? Okay, so I think that's a pretty good place to stop. So as always, if these lectures are not sufficient, you can see where I'm at in the book. So make sure that you're following along in the book. If I haven't sufficiently delivered enough information, that's going to happen, okay? And then on the third and final video, we'll go through the naming of compounds. And that's going to be probably one of the biggest things from this chapter is how to name these compounds. Because everything we do from here is going to be based on how well you know how to name these compounds. So that we can talk to each other, right? So we know what we are talking about when we say the names of these compounds. Okay, folks, I'll see you in the third and final video for this week.